Okay, good Monday morning to you all. We're going to move on to chapter 20 today, where we're going to start talking about how you do reactions with benzene rings. We spent part of last week talking about the special stability you get from aromaticity. We talked about what that was. And now we're going to deal with how you start to do reactions with benzene. And the class of reactions we will talk about is called electrophilic aromatic substitution. So it's going to be a substitution reaction because we're going to replace a carbon-hydrogen bond on the benzene ring with a bond between carbon and something else. So the pattern for what we're going to talk about today, most of these reactions that we'll deal with follow this same theme. So just as with carbonyl chemistry, you learned a ton of different reactions, but actually it was only one or two mechanisms. We're going to see the same thing today. So we can use benzene as a nucleophile. Remember that you've got a low energy orbital that's filled, and then you have two equal in energy, higher energy orbitals, and it will be one of these two pairs of electrons that will do the reacting. It doesn't matter which, they're equal in energy. But the way we're going to show that is I'm just going to draw an electrophile here, and we're going to pretend that we don't care what the electrophile is. Pi electrons from benzene, doesn't matter which ones, will attack the electrophile. If you look at what happens there, what we'll have is an intermediate in which we formed a new bond between carbon and the electrophile, and then there is a positive charge on the other carbon that was involved in the pi bond that we used to attack the electrophile. And then you might expect this carbocationic intermediate to be unstable, and it is. It's resonance stabilized, but the big problem here is it's not aromatic. So you can imagine losing aromaticity here is very costly energetically. This is a high energy intermediate, so your electrophile needs to be really reactive. And so we're going to show you some electrophiles today that you haven't encountered before, but they're super electrophiles. Then the final step is downhill. You require a base, but it can be even a very weak base. You don't even have to worry about actually generally what this base is. We don't add a base to the reaction. Generally, it's a counter-ion or something. We'll remove this proton, electrons kick back down, and we reestablish aromaticity. And in the end, if you look at what we did, we swapped out a proton for our new functional group that we put on the benzene ring. Okay? So today we're going to talk about what these electrophiles are and how they influence reactivity of the benzene ring. We'll also talk about things you can do once you've installed something on a benzene ring. So example one of a reaction is aryl halogenation. That is, we're going to use Br2, and then it turns out we're going to need something else as well. And this is iron tribromide. This is just the iron tribromide is a Lewis acid. It's got an empty orbital on iron that can accept electrons. The effect of this reaction will be to put a bromo group on one of the carbons of the benzene ring. And let's look at what the electrophile is. So first, you have Br2, and you have lone pairs on Br2 that can coordinate with the metal. So this is the generating the electrophile part. And what we're going to draw here is going to be something that's kind of weird. If you follow the formal charge, the bromine that's now bonded to two things has to have a positive formal charge, and the iron will have a negative formal charge. It was neutral before, but we put electrons on it. In any case, what this does is it makes a super electrophilic bromine. You'll recall in 351 that you did reactions with an alkene attacking bromine, and there Br2 was sufficiently electrophilic, and the bromine-bromine antibonding orbital was low enough in energy that an alkene could attack it to make a new bond. And the reason this would work is, of course, that Br- was a good leaving group. Now, see what we're going to do here. You can imagine that if Br- is a good leaving group, that that once that Br is coordinated to something else, this is even better of a leaving group. So green is for super good leaving group. And you'll be able to see why once you see what it is after the leaving group leaves. So we'll now have the benzene ring attack the Br on the end there, and leaving group leaves. That gives us the intermediate in which we are no longer aromatic and we have a positive charge adjacent to the carbon where the bromine was installed. The thing that leaves is FeBr4-, and that negative charge is likely shared by all of the bromines. And then finally, we can have some base, and it's probably a Br- somewhere, possibly from FeBr3, or sorry, FeBr4-, but we won't ever really worry about what this base is because it's so easy to remove that proton. Doing so is downhill in energy and restores aromaticity. Okay, so that's first example of something with a benzene ring. You're using iron tribromide as a Lewis acid to activate Br2 to make it super electrophilic. All right, questions so far? You can do this with chlorine too. So we could take a benzene ring, Cl2, FeCl3. Usually, people always ask, why do you have to match the identity of your halogen with the other groups on the iron? I don't know, but your book always does, so we'll just sort of stick with that. Nevertheless, there aren't going to be any options on an exam in which I tell you, oh, do you want to use this or do you want to use this? Because that would be silly. We've got more important things to worry about. All right. One thing we could do at this stage is just ask, how do these groups affect the reactivity of the benzene ring relative to the benzene starting material? Chlorine is electronegative, and we'll put bromine in that group too, even though bromine's a lot less electronegative than chlorine. So in electronegative, I guess that's an okay abbreviation, I don't know. So you would expect them to withdraw electron density from the ring, and they will do this because of their increased electronegativity relative to carbon. They will do this through the bonds via something that we call an inductive effect, and I think you learned about that in 351 in the chapter on acid-base chemistry. So what will happen then is that rings that have halogens on them are going to be less reactive than benzene. Now there's another issue that we'll talk about in a little bit, and that's the idea of if you already have something on a benzene ring, where does the next thing go? In addition to their ability to withdraw electron density by electronegativity, the other thing you have to notice about these halogens is you have lone pairs adjacent to the ring. And so these groups with lone pairs adjacent to the ring can be resonance donors. That's not going to matter in terms of benzene's reactivity. The electronegativity effect dominates for the halogens. These rings react, rings that already have halogens on them will react more slowly than benzene rings, but you do have this other resonance effect that we'll talk about in a little bit. Okay, other questions you want to ask at this stage? All right. So the next one that we're going to talk about is installing a nitro group. We call this aryl nitration. Your text will show you how to generate the electrophile here. I don't particularly care about that. The conditions for this reaction are using nitric acid in sulfuric acid. Usually when you mix nitric acid and sulfuric acid, you've got something that's called aqua regia, or fuming sulfuric acid. It's kind of a dangerous thing to do, so I've never done this reaction and wouldn't necessarily recommend it. But if you want to install a nitro group, that's how you do it. These conditions of nitric acid and sulfuric acid allow you to generate the following electrophile, NO2+. Your text will show you how to do that. It's really not hard, but it's sort of pointless, and we want to avoid unnecessary details. So if you want to know more about that, I'll refer you to the text. But you generate this NO2+ as the electrophile, and then, just as we've done previously, pi electrons on benzene attack the electrophile to give you the no longer aromatic carbocationic intermediate. Probably instead of just drawing the arrow to nitrogen, we'd have 5 bonds to nitrogen if we stop there, so we need to push one of those nitrogen-oxygen pi bonds. We need to break one of them and put the electrons out on the oxygen. The nitro group that we've installed will look like this, and we'll have a positive charge on the adjacent carbon. Questions about that step so far, what we're doing there? Yes?
Remind us something about it. So HNO3, and I'm only seeing 2 oxygens.
HNO3 and you're only seeing 2 oxygens, yeah. So what happens, let's see, nitric acid is this. And with sulfuric acid, you put another proton there. That becomes a good leaving group. We kick those off, and that generates NO2. So that's where it goes. But we're not going to worry about that a lot. Other questions? This step here is not so very much different from carbonyl chemistry. You can think of this as, if you imagine this as a carbon-oxygen double bond, then having an electrophile attack at the electron-deficient carbon and breaking a pi bond would have made sense. Once you put the nitro group on, probably water is a sufficiently good base to remove the proton, and that gives you nitrobenzene. All right, so let's talk about the nitro group and what its effect is. I'm going to draw the Lewis structure of the nitro group so that you can see an important pattern here. In the nitro group, this negative charge on the oxygen is delocalized between the two oxygens. You have a positive formal charge on the nitrogen, so overall the nitro group is neutral. The nitro group, you have the nitrogen that is electronegative. So this is an inductive, what we're going to call EWG stands for electron withdrawing group, meaning that you've got a dipole that pulls electron density out of the ring. But there's something else that can go on too, and it is that the nitro group, let's put NO2, is also a resonance electron withdrawing group. What do we mean by that? Well, and this can happen anytime you have the thing that's bonded to the benzene ring also involved in a pi bond with an electronegative atom. When that occurs, it's very easy to draw a resonance structure in which I actually pull electron density out of the ring and out onto the nitro group. You see how we get from here to here? We simply take the some of the pi electrons from benzene, move them over to become a new pi bond between carbon and nitrogen. Nitrogen still bonded to four things, still has a positive formal charge, and then we break that pi bond and move it out onto the oxygen. Okay, so you would expect nitro to be a really good electron withdrawing group because it has both that effect, both in terms of resonance and through electronegativity. So nitrobenzene is less reactive than benzene. Another thing I want to point out at this stage is just that because of the nitro group, not all of the carbons in the ring are similar in reactivity. The nitro group could put a positive charge in the ring, and we can draw resonance structures in which that positive charge is on the carbons adjacent to the nitro group and the carbon opposite to the nitro group. So, I'll highlight the carbons that are especially electron poor due to the presence of the nitro group. We will have a way of talking about these carbons that are adjacent to other groups. We'll call them ortho. So if you want to number around the ring 1, 2, 3, 4, 5, and 6, carbons 2 and 6 are called the ortho positions. Carbons 5 and 3 are called meta. And then carbon 4 is called para. All right. And we'll use that a lot as we talk about benzene rings that have more than one thing on them. But for right now, I want you to see that because of the electron withdrawing nature of the nitro group, the ortho and para carbons are especially electron poor. Okay. Questions about that? Yes? Is there any reason not to use alpha, beta, gamma? Sure. Well, no, not in particular. I don't know why they chose that. These are, I'm not sure whether the ortho, meta, and para are from the Latin or the Greek, but they mean something to somebody at some point. So, sorry. Sometimes nomenclature seems to have been designed to make things as unintelligible as possible. But if you think this is bad, just wait till biochemistry, where every protein has an acronym for a name, and then you have to. There's no rhyme or reason to that anyway. So anyway, what else? What other questions? Yeah.
So was the halogenated benzene, was that less reactive as well?
Yeah, the halogenated benzene is going to be less reactive than benzene because of this inductive effect. Now we're going to see some, I told you that these lone pairs on the halogen can donate electron density into the ring. That will be important later, but it's not enough to compensate for the inductive effect that makes the ring a little bit less reactive. Others? Fortunately, among the groups we will consider, it's only the halogens where the inductive effect offsets the resonance effect. Everything else sort of fits into a better or a simpler category. Okay. So what if we have a nitro group in place and we do a subsequent reaction? Where does the next thing end up? So let's start with nitrobenzene, and then let's do the bromination reaction. Okay, and we could consider 3 possible products, the ortho, the meta, and the para products as possibilities, though in practice we do not observe all of these. We only observe some, or one, depending on the situation. Holy Toledo, that's not ortho. I'm sorry, I get that from my father-in-law. He says that all the time, so it's become part of my vocabulary. I don't know whether Toledo, either in Ohio or the one in Spain, is holy. I just know that I think in the old Batman cartoons, that used to be an exclamation of surprise, either on the part of, no, not the cartoons, the original live-action Batman stuff from the 60s, I think. Batman or Robin said, "Holy Toledo." So, whatever. All right, so which of these do you expect to be the major product? And for that, go back to this resonance structure and the reminder of which carbons are electron poor. Okay, so what do you think? Remember, in this reaction, go ahead.
So I was thinking that maybe the meta one would be the major product, just because if there's a positive charge on all the other carbons, it will be less likely to act as a nucleophile. Okay, good. In the reaction, the benzene ring is the nucleophile. You want electron richness, not electron poorness. And the ortho and para positions are more electron poor. So yes, indeed, the meta product is the one that we observe, and not the other ones. And that is what we mean by regioselectivity. These are regioisomers or constitutional isomers, but we only see one. All right, go ahead. Do you ever see, though, that it can now act as an electrophile because it has those positive spots?
Do we ever see that a benzene ring can actually act as an electrophile when it has those positive spots? Yes, there's a whole class of reactions called nucleophilic aromatic substitution. We're not going to talk about them. We'll just sort of skip over that. Yeah, they are important, but we got a ton of important stuff to talk about. All right, other questions? Yes?
This is going back a little bit, just debating it, we couldn't really understand it. Why does the bromine and the chlorine and the nitrogen electron withdrawing group make it less reactive?
Why do these things, the chlorobenzene, bromobenzene, nitrobenzene, why are they less reactive than benzene? remember that in these reactions, benzene is the nucleophile. So if you make the ring less electron rich, you're going to slow down the reaction. And for all of these, for bromo, chloro, and nitro, you've got this withdrawing effect. For bromo and chloro, it's due to their electronegativity. For nitro, it's due both to their electronegativity, both to its electronegativity and the resonance effect. But that tends to make the ring less reactive because it's less electron rich. Yeah.
So would this also make the carbon that is would it make the other remaining carbon less reactive if you add that bromine group to major?
So once I add the one bromine group, does it make, is bromo-nitrobenzene less reactive than nitrobenzene? Probably. Nevertheless, if you did a subsequent reaction, whatever you put would be on the metacarbon.
Okay.
Yeah. Yes.
So I understand that the benzene ring becomes less electron rich,
Uh-huh.
but that opens it up to that other class of reactions that you just talked about.
That's right. If the benzene ring is more electron rich, it does open you up to the other class of reactions that we talked about. So that can be synthetically useful. Yeah. Go ahead.
So this reaction that we just did, where we started with the neutral group, does that work the other way around as well? If we start with like a bromo.
Ah, okay. Does it work with meta substitution if you start with the bromobenzene? Hold on. Because that issue of, remember with nitro, you've got withdrawing via both sort of effects, inductive and resonance. With bromine, you've got some offsetting things there. And so we'll talk about that in just a second. One other way you can understand why the meta product is favored is to think about the stability of the carbocationic intermediate that would have led to each of these products, right? So we are running out of space. So we'll just shrink it. Okay. So the intermediate that would have led to the meta product would look like this. You've got the nitro group there, and Br is here, hydrogen's there, positive charge is there. Now, we could draw resonance structures where we would put that positive charge on the carbons that I've highlighted in purple. And you convert from one of those to another simply by moving one of the pi bonds, right? I'm not going to draw all of those resonance structures. But the point is that in this carbocationic intermediate, the positive charge that we introduce by having the benzene ring attack the Br, that ends up never directly adjacent to the nitro group. In contrast, let's draw the intermediate that precedes the para-bromo product. We have a positive charge here, nitro group here. That positive charge is going to be delocalized, and one of the resonance structures is going to have that positive charge immediately next to the nitrogen, which is already withdrawing electron density from the ring. And so you might expect that to be very unstable to have the positive charge adjacent to such a strong electron withdrawing group. The same would be true for the ortho substitution intermediate. If we put the Br on the ortho carbon, again, we have a situation where that positive charge is delocalized, and in one of the resonance structures, it would be adjacent to the nitro ring. So both of these intermediates that precede the ortho and the para products are very unstable because they put the positive charge adjacent to the nitro group. The meta just happens to be the best solution you can come up with because at least the positive charge is not adjacent to the nitro group. Okay, questions about that? So you can understand this regioselectivity pattern by considering in the starting material which carbons are electron poor versus rich, and for the nitro group, the ortho and para carbons are electron poor and therefore less reactive, and you can consider the stability of the intermediate and where the positive charge is, and if you go through the meta substitution pathway, that positive charge is never immediately adjacent to the nitro group. All right. Other questions? Yeah.
So just to clarify, we don't see the other two products because the intermediates are too unstable.
Right. We don't see the other products because the other two intermediates are unstable. Asterisk. Because if you do any of these reactions in the lab, you will get a percentage of this and then smaller percentages of these products. And presumably you can separate them and get the desired product out. So for this reaction, if this were predict the products like on your practice exam, you would only draw the meta product as the product of this reaction. Now let's deal with the question about what if we started with the BR. Remember what I told you about bromine and chlorine. Maybe let's just use chlorine because we haven't done a lot with chlorine yet. I told you that chlorine is an electron withdrawing group via an inductive effect, but it is an electron donating group via resonance. And the reason it's an electron donating group via resonance is because I can draw a resonance structure in which I move lone pair electrons from chlorine and make a new pi bond between chlorine and carbon, and then I would have a negative charge on this ortho carbon, and I could draw resonance structures where it was on the para carbon. Now, that resonance structure looks bad because, and it is, because chloro is electronegative. And so this resonance structure doesn't contribute much to the reactivity of chlorobenzene, which is why the electronegativity effect dominates and chlorobenzene is less reactive than benzene. But when you get to a carbocationic intermediate, the resonance structure where chloro donates electron density into the ring starts to look quite a bit better. So let's draw what the intermediate would be in the following reaction. Here's chloro, we're doing the nitration reaction, and we want to determine whether we're going to get ortho, meta, or para substitution products. So let's draw the intermediate that would come from ortho substitution. Notice that that intermediate puts a positive charge adjacent to the chlorine. Now that may look bad because chlorine's electronegative, but when push comes to shove, I will send a fully armed battalion to remind you. We went and saw Hamilton this weekend. My son, I don't know if I told you, I'm pretty sure I did, about acting in a fifth grade play version of Hamilton, and so this was like his dream come true, and it was really quite good. But now it's in my head constantly, and so it just comes out. Notice that when we have that positive charge, the electrons from chlorine can stabilize that positive charge via resonance. This resonance structure looks okay in the sense that at least the positive charge in the ring is delocalized. Okay? So we will see that in terms of regioselectivity, For benzene, for chloro and bromobenzenes, the electron donating effect is more important. But for reactivity, faster or slower than benzene, the inductive effect is more important. So yes, chloro and bromo are going to be what we call ortho and para directors, in the sense that the intermediates that precede ortho and para substitution are stabilized by resonance. I'll illustrate that by drawing the two other intermediates, and again, hopefully you can see that the positive charge in these ortho and para substituted intermediates will be adjacent to chloro, which can donate in. In contrast, the meta substitution product would put the positive charge in a place where it cannot be stabilized by chloro. Right. So it turns out that when we use the halogens as chlorobenzene or bromobenzene as starting materials, we get ortho and, oh, that's a bad ring, ortho and, man, it just gets worse. I need to stretch out my hand. There we go. We get the ortho and the para substitution products and not the meta substitution. Now, in actuality, when you run this reaction, are you going to form ortho and para in equal amounts? Probably not. You've got a couple of things going on here. First, there's 2 orthocarbons. There's only 1 para carbon. So statistically, you might favor ortho, but sterics should favor para versus ortho. And it's sort of a case-by-case basis. I won't ask you to ever predict whether ortho or para will be major relative to each other, just that both of them will be present more than the meta product. If you were doing this, if you were using a synthesis, I would allow you to use either of these in a subsequent step, assuming that you could purify them away from each other, and then you'd be good to go. Okay? Yes?
Will the second exam be multiple choice as well?
Will the second exam be multiple choice as well? Yes. That gets you guys feedback fast, and it makes it easier for me to give partial credit in retrospect, and then everybody gets it instead of just the intrepid few who come to my office and do battle with me in requesting points back. It's actually not that bad. I'm kind of not mean most of the time. All right. So I want to show you a cute little reaction we can do after we install a nitro group. And we're doing this because it's a way to convert what was an electron withdrawing group into a very strong electron donating group. So it turns out that you can use hydrogen and palladium on carbon to reduce the nitro group to an amino group. The mechanism of this, I don't know it. It's not particularly important. You're using hydrogen and palladium on carbon, the same conditions we used to reduce alkenes previously, and they're reducing the nitrogen-oxygen bonds to nitrogen-hydrogen bonds. Notice that these hydrogenation conditions do not reduce the alkene, do not reduce the pi bonds in the benzene ring. That is because of aromaticity and the special stability that benzene has. The product of this reaction has an amino group on benzene. Molecules that have amino groups attached to the benzene ring are called anilines. And so I will use that term in class because it's shorter than saying a benzene ring with an amino group on it. But you don't need to necessarily worry about that as long as you understand what it means when I'm talking about it. The amino group is an electron withdrawing group via an inductive effect. But that is only a minor issue for the aniline. It's an inductive donating group via resonance, and it's a very strong inductive donating group. So what this means is aniline is more reactive than benzene. It will react faster than benzene because of the electron donating effect, and in terms of regioselectivity, it's going to be an ortho and para director. And you could draw a resonance structure in which you donate electron density from the aniline nitrogen into the ring. So you would predict that ortho and para carbons are electron rich. And then you would also, if you were talking about, or if you wanted to do a reaction with the aniline, you would see, as we've talked about before, that if you do ortho or para substitution, that puts the positive charge adjacent to the amino donating group, where it can be stabilized by resonance with the lone pair that's on the nitrogen. So if we were to do a subsequent reaction, say the chlorination reaction, where would the chloro go for the aniline? Which carbons am I going to put the chloro on? Ortho? Okay. How about para too? Yeah. And we're not going to worry about the selectivity between ortho and para. They come together, and that's all. We'll draw both of them as products. So yes, we're going to install chloro here, and we'll also get the para regioisomer. Okay. So this reaction actually allows us to think a little bit strategically in synthesis. What if I told you I wanted to make this as a product? And I wondered what the starting material was and how you got from that starting material. Well, actually, I'll tell you what the starting material is. It's benzene. How do we get from benzene to that product? And when you're planning a synthesis of a benzene ring, it's useful to look at the two groups that or multiple groups that you've got on the benzene ring, and think about what their natures are in terms of regioselectivity, so you can sort of plan which one had to come first and which one had to happen second. So what about the amino group? We know that it's an ortho and para director. We know it's an electron donating group via resonance. The bromo group we also know is an ortho and para director. But we see that the two of them are meta to each other, which is a problem, because if I put the bromo on first, then anything I do after that is going to prefer ortho and para substitution. If I were to start with the aniline with the NH2 already in place, anything I do after that is going to prefer ortho and para substitution, but they're meta to each other. So now we have to think, is there a solution? Go ahead.
Start with NO2, right?
Right. Why not, instead of worrying about the aniline to begin with, let's use nitration to put the nitro group in place. Then let's do bromination to put the bromo group meta to the nitro, because nitro is a meta director. Running out of space again. Then, after we get to the meta nitro bromo benzene, we could use hydrogenation over palladium on carbon to reduce the nitro group to the aniline, and there we've got our solution. Yes?
Why do you put the bromo group on before you use H2?
Why do I put the bromo group on before I use this?
Yes.
Because if I converted nitro to aniline, aniline's an ortho-para director, so I would have gotten the bromo here or here instead. Yeah, so you use the nature of each group and where they are relative to each other to figure out the order. Another question, why would it have been a problem to do bromine first? Go ahead.
Isn't that just because it's ortho-para director?
Exactly. If you did the bromination first, then when you go to put nitro on, it's going to be ortho and para instead of meta. Is that your question?
Is there a way to oxidize an aniline back to a?
Can you oxidize the aniline to the nitro group? There is a reaction you can do with the aniline, and it used to be in the Smith text. It's not anymore. I don't think you can convert it into a nitro directly, but you can convert it into something that looks like this. And that actually is a great leaving group. So, but yeah, I don't think we're going to go there this time. Yep. All right. What else? Yeah.
So what is it about the NH2 versus the NO2 that caused one to be ortho-para and the other one to be meta? I didn't quite see what.
Yeah. So the difference between the two is that the nitro group, in the nitro group, the nitrogen's involved in a pi bond to oxygen, which makes it a withdrawing group because we can take electrons from the ring and move them out there. With the aniline or the amino group, we don't have any pi bonds. Instead, we have a lone pair. So instead of withdrawing density into the ring, we can donate it into the ring. Yep, and that's the key difference. All right, well, happy Valentine's Day. Such as it is, go do your homework.